Hey guys, this is Johnny the Organic Tutor. Today we're going to be discussing something called chair conformations. So let's just go ahead and jump right into what a chair conformation is. So a chair conformation is basically, it's going to be a 2D representation of a 3D cyclohexane. So we're just going to be talking about cyclohexanes in this case. Let me use a different color. So as we all know, a cyclohexane looks something like this. It's a 6-carbon ring, and each of these carbons right here, these are going to be sp3 bonded, because they're all single bonded. So each of these have 3 regions of electron density. All right, so now that we know what a cyclohexane is, let's see how we can convert one of these into a chair conformation. So when we're talking about chair conformations, we're going to be talking about a di-substituted cyclohexane. So a di-substituted cyclohexane. That just means that on 2 carbons, we're going to have substituents. Any more than that, you can still make a chair conformation, but you'll see in a later video, we're going to basically be using a chair conformation to determine the stability of a given cyclohexane or chair conformation. And that can only be done, or is typically done using a di-substituted cyclohexane. All right, so what do we need to know about the cyclohexane in itself first? So let me redraw this. So let's just number our cyclohexane like this. So we know with a typical cyclohexane, all these carbons are going to have hydrogens attached. But let's say we have a substituent on one of them. Let's say we have a chlorine on this one, and on this one we have a bromine. Because these are sp3 carbons, meaning they have 4 different groups attached to it, or lone pairs, but in this case, they're going to be groups. That means we also have a hydrogen here and a hydrogen here. That makes these 2 carbons chiral carbons. So if you don't know what a chiral carbon is, it's basically just a carbon with 4 totally different groups coming off of it. And when you have 4 different groups coming off of it, you have to assign stereochemistry to the bonds. And that is basically just the orientation of whatever bond you're talking about. So the chlorine can be going in a different direction than the hydrogen, and we'll see how we do that right now. So if we have a wedge bond, so it looks like that, this means that the bond is coming towards us. If we have a dash bond, that means the bond is going away. So now let's redraw the bonds on this cyclohexane. So let's give chlorine a wedge, and then let's give hydrogen a dash. And then let's do the opposite on this one. Let's give bromine a dash and hydrogen a wedge. So now these 2 carbons have stereochemistry. So on this carbon, on carbon number 1, we see the chlorine is going to be coming towards us, the hydrogen is going to be going away from us. I'll make a new video on stereochemistry later, but that's all you need to know for now. And on carbon 2, the bromine is going away and the hydrogen is coming towards us. And stereochemistry is just something you need to define when you have chiral carbons, because it does make a difference in naming the molecule. It makes a difference in the properties of the molecule. It basically there's 2 versions of a molecule with 2 different versions of stereochemistry. And I'll talk about that in a different video, but just know that for now. All right, so the main thing we're going to do is we're going to convert the cyclohexane, the 3D, so this is what is drawn up here, into a 2D chair conformation. And I'll show you what a chair conformation looks like. Let's look at the format of one, or the shape. So this is what a chair conformation looks like. Just kind of like a bow tie, but tilted to the side a little. And this is kind of just preference, how you want to number the carbons in your chair conformation. I always start right here in the top right and go this way. So 1, 2, 3, 4, 5, and 6. Let me get rid of this so I can draw in the bonds. And then I'm also going to draw in, this will make sense later, but these placeholder bonds that are coming off of each of these carbons. So on carbon number 1, it's going to look like that. Carbon 2, going to look like that, and so forth. So something to notice, on carbon number 1, the up position, which is this one, is going straight up. But on carbon number 2, the up position, which is that one, is slanted. So when they're straight up, that is called axial. That's the axial position. So that is just vertical. And then if they're if they're slanted like this, that is called the equatorial position. And that will be important later when we talk about the stability of the chair conformation. All right, so that's your basic format right now. Now we're going to be talking about how we can actually put the bonds of the cyclohexane onto this chair conformation. So let's use that same example we did earlier. Actually, let's come up with a new one. So on this one, let's say we have a Br and a hydrogen. All right, let's say we have something like this. Now, when I number my cyclohexanes, I do it how I would name it. So I'll also make another video on how we're going to name molecules, but we know that when we're naming, our parent is going to be this alcohol right here. So that's where I'm going to start my numbering, and I'll go into detail about naming in the future. So 1, 2, 3, 4, 5, 6, like that. All right, so now we have our cyclohexane. This is our 3D structure. Now, how are we going to convert this into our 2D chair conformation? So let's draw our format, and then let's also draw in those placeholder bonds that we have. All right, and just like before, I'm going to put one up here and go all the way around. So now let's think about what this would look like if this was just a regular cyclohexane that looked like that. So we know all of these have just hydrogens on it, right? So that basically means that all these placeholder bonds are going to be hydrogens, right? And so forth. All right. Now, what if we have something other than hydrogen? Well, then something other than hydrogen is going to go on these bonds, and the rest of the bonds are going to be hydrogen. So they're not technically placeholder bonds because they will have something attached to it, but we don't need to draw in these hydrogens because it's assumed that if there isn't anything else bonded to it, there has to be hydrogens onto it, connected to it. All right, so now let's look at this cyclohexane up here. So what I do is I start at carbon 1, and I go 1, 2, 3, 4, and look at the substituents on each carbon in order of how it's numbered. So on carbon 1, up here, we have an OH, an alcohol, on a wedge bond. So I'm going to write that. So on carbon 1, we have an OH on a wedge, and then we also have a Cl, so a chlorine, on a dash bond. And on carbon 2, we have a bromine on a wedge and a hydrogen on a dash. So like I said before, a wedge means that it's coming towards you or towards you from the plane, so it's not level with the plane, and the dash means that it's going away from you, so it's also not in level with the plane. Now, if you don't have a wedge or a dash, you'll just have, you know, a straight line like this. This means that these bonds are in the plane. And if you want to understand that better, I would suggest getting a modeling kit. You'll see how sp3 shapes really exist physically, whether the bonds are in the plane or they're going away or towards you, and it's also very useful for stereochemistry. All right, so we also need one more piece of information before we can draw this. So we need to know whether the wedge bond is going to be in the up position, or whether the wedge bond is going to be in the down position. So we're going to, I'm going to draw a wedge bond and a dash bond. So the wedge bond is always going to be in the up position, and the dash bond is always going to be in the down position. So now we can draw in our chair conformation. So on carbon 1, we have an OH on a wedge bond. So that means it's going to be in the up position, right? All right, so let me use a different color. So on carbon number 1 right here, we have an OH going up, so that's going to look like that. And then we also have a chlorine on a dash, which means that it's going down. So that's going to look like that. This bond right here is going down. I didn't draw it going down as much as I should have. And on carbon 2, we have a bromine on a wedge, which means that it's going to be in the up position. So that means it's going to look like that. And then a hydrogen in the down position because it's on a dash. So this is your filled out chair conformation. Now, if we want to just simplify it, it will look like this. And then this is going down. And I'll draw on the hydrogen. So remember, we don't need to draw on the rest of these hydrogens. So on these carbons right here, these are all just hydrogens, remember? All right, so this is, let me show that. This is your filled out chair conformation. As simple as it can get. So this is how you're going to convert a cyclohexane into a chair conformation. And in another video, or in the next video, I'm going to be going over how we're going to be doing something called a ring flip. And then from that, we're going to be determining the stability of that chair conformation. This has to do with what bonds are equatorial and which bonds are axial. So a very, kind of a precursor to the next video, we're going to be talking about stability, because we are going to be doing something called a ring flip. So this is how we're going to be determining the stability. And this all has to do with which groups are equatorial and which are axial. Let's see. Why don't we do one more example? So, let's have something like that. And let's have a methyl group and a chlorine, and then on this one, let's have that. All right. You know, if you like to use skeletal formation or skeletal structure more, and you don't want to call the CH3s, CH2s, and all that, I'll draw it out like this. So just a methyl and a propyl. Let's see. So just like before, I'm going to number these based on how I would name it. So again, alcohol is our parent. So 1, 2, 3, 4, 5, 6. And let's go ahead and one, 2, 3, 4, 5, 6. I'll go ahead and put in my placeholder bonds. All right. This format right here, it really is just something you should memorize. These things really just do take practice. Knowing this is really probably, you know, half of converting these into chair conformations. The other half is knowing that a wedge bond is going to be up, a dash bond is down, and, you know, and then just making sure the substituents are on the right carbons going from your cyclohexane into your chair conformation. All right, so now let's look at carbon number 1. So that's this carbon right here. So carbon 1, we have an alcohol going on a dash, so that is in the down position. And then we have a propyl group, that's the CH2, CH3 group, and that is on a wedge, so that's in the up position. So we can draw those in. So in the up position, we have propyl. In the down position, we have our alcohol. All right, halfway done. And now on carbon 2, I'll do that up here. We have a methyl, so just that CH3 on a wedge, so that is going up. And then we have a chlorine on a dash, sorry, so that's going down. So remember, we need to match carbon 3 on the chair conformation with carbon 3 on the cyclohexane. So before, we had it on carbons 1 and 2. So, you know, we had carbons 1 and 2, and then carbons 1 and 2 here. But now, since we have them on carbons 1 and 3, they're going to be separated. They're not going to be right next to each other, so we have to make sure we put it on carbon number 3. So go in the up position, we have that methyl, so we can draw that in. In the down position, we have that chlorine. So this is your completed chair conformation. All right. So I hope this video helped. This is just the first step of chair conformations. The next video goes more in depth about the actual purpose of chair conformations with regards to stability, ring flips, and basically why we use chair conformations for cyclohexanes, which is probably the more important part. But this is a good start. If you have any questions, leave them in the comments. And in the next video, I'll be explaining a lot more, so you can click on that if you need to learn more about these chair conformations. All right, guys, take care.